Now,
Recording in progress.
focus. Let's begin with our first problem for today. You're given an array of size n. Let's say the elements that you were given are something like this: 8, 17, 5, 12, 20, 3, 13, or instead of 13, we'll go 21 and 9. You're given an array of size n. So here, the question is something like this. This is a two-player turn-by-turn game. This is a two-player turn-by-turn game. In any player's turn, a player can pick an element from either ends of the array. A player can pick an element from either ends of the array. Means whoever plays first, they can either choose to pick 8 or 9. Let's say the first player goes with 9. Now the second player can pick either 8 or 21. Let's say the second player goes with 21. Now the first player can pick 8 or 3. Let's say the first player picks 8. Now the second player can pick 17 or 3. In this manner. So only from the ends of the array, you can pick one of the elements. The objective of this problem is not to check who will win the game, but it is more like what is the maximum sum player 1 can get. What is the maximum sum? Player 1 is nothing but the first player. Player 1 can get if both play optimally. What is the maximum sum player 1 can get if both play optimally? Write in the question properly first, and then we'll discuss how to approach this. Please don't share any solutions in the chat until I ask you to share. All right, ideas? Ideas, observations, whatever you have, you can share. Selecting the maximum number every time. Player 1 chooses maximum and player 2 will choose minimum. Player 2 will not do that. Player 2 will also play optimally. Both the players play optimally, right? Optimally, not in the sense that player 1 to get the maximum sum. Optimally in the sense that both will try to get the maximum sum for themselves. See, guys, a greedy approach here. If you just trace it out for the first one or two examples, you'll realize it doesn't work. See, when first player has the option to choose 8 or 9, if you go with 9, then player 2 is picking 21. See, just with the first element itself, your theory is failing. You should have verified it before sharing it with me. And if you continue doing that, now again, player 1 will pick 8 because 8 versus 3, right? Player 1 will pick 8. Player 1, I'll mark it in red. Player 1 will pick 8. Then player 2 will pick 17. Now, if you say that, okay, no, I will not check just 8, I will check 8 and 17, I will check 9 and 21, and then I will decide. Then you are extending your greedy by one more step, that's it. Instead of checking the greedily over here, you're checking greedily over here. That is still not going to work. A greedy approach is a local optimum. We don't want a local optimum here. We want a global optimum here. So choosing max on both sides is clearly a very bad approach for us. A greedy approach is a very bad approach for us here. Player will choose a number only if it will make the sum greater than player 2 sum. Not necessarily. Both the numbers initially, because player 2 has a 0 sum, both the numbers are good. Then again, if you say that, okay, I'll pick whichever is bigger, then the same story repeats. So basically, we need to figure out what is the optimal way, what is the global optimum here. We need, so as Samarth mentioned, we have an optimal substructure here. But how do you break down this problem first? How do you understand this problem in a more DP-like way? So we'll start with these usual dashes that we have. Now it's not about, you are at ith position or ith position, right? That is not your, middle of the problem. What is the middle of the problem? You are left with some I to j elements. That is the middle of the problem here, right? Some I to j elements are left. Index I to index j elements are left. That is the middle of the problem here. So using index I to index j elements, what is the maximum sum that the current player can get? That is how we need to start thinking now. Using all the elements from index I to index j, what is the maximum sum the current player can get from here? So let's call this situation as f of I comma j. F of I comma j is basically what is the maximum sum the current player can pick in the range I to j. Now, there are two options here, right? Pick I or pick J. If you pick I, what is the remaining subproblem? If you pick I, what is the remaining subproblem? That's right. I plus 1J is the remaining subproblem. And if you pick J, what is the remaining subproblem? That's right. Perfect. Ij minus 1. Ij minus 1. Ij minus 1. Perfect. So now this is where things get tricky, guys. This is where you need to pay a bit more attention, okay? Why do we write this step? Why do we write remaining subproblem step? To understand if you pick I, what is the best you can get from the remaining subproblem? Or if you pick J, what is the best you can get from the remaining subproblem? Right? That's what we did all these days. But these two subproblems that we have here, let's say this is done for player 1. This is a subproblem not for player 2, right? That is the state you are giving to player, sorry, that is the state not given to player 1. It is given to player 2. So you can't say that whatever is the best for player 2, I will do that. That is not optimal. At the same time, you can say that whatever is not best for player 2, I will do that. Because you don't know what player 2 will do after that. You don't know if player 2 will give you one of these two states or one of these two states. But you know that player 2 is going to give you only one of these four states. No other state is possible. If player 2 picks I there, then it will become I plus 2J. If he picks J here, it will become I plus 1J minus 1. If he picks I here, it will become I plus 1J minus 1. And if he picks J here, it will become IJ minus 2. Only one of these four states are possible for player 2 to give you in your next turn. Now you need to think like this. Okay, now when I am here at I to J, this is not my subproblem. That is player 2 subproblem. This is my subproblem again. At I to J, this is not my subproblem. That is player 2 subproblem. But the problem here is player 2 will make sure that out of these two states, for example, let's say you picked I and you give this to player 2. Out of these two states, he will give you whichever is the minimum. Exactly. He will give you whichever is the minimum and he will give you whichever is the minimum. Because he wants to play optimally. He wants to make sure your sum is minimized at the same time while his sum is getting maximized. So obviously for us, out of these two minimums, we want whichever is exactly, whichever is the max, that is what we want. So for the current player, this is not his subproblem, that is opponent's subproblem. This is the current player's subproblem. But because it is in opponent's hands, in depending on him which state we are getting, we know that he will try to minimize it. So out of this minimum and this minimum, which is the minimum that we want, we need to choose that. Make a note of it till here, then we'll discuss more. Exactly, max of the two mins. here we are talking about future outcomes, right? This is not future because in each step, the array size is reducing. So I plus 2j is not future here. In fact, it is still past itself. So I think the definition of future and past that we have is different from the future and past that we are discussing here. So it's not about so this is like, this is a state that is essential for you to, or this is a state that is essential for you to compute this state. So this is a state that you will compute first, and then you will compute this state. So if you go back to our previous type of problems, the old type of problems, whenever you have an array and when you are at an ith step, you're what do you say? You're thinking that, okay, using these, how can I compute these? So what are my options here? And what is the best I can do with the remaining I minus 1? So how you are computing it? Are you doing a memoization and coming top down, or are you using tabulation and coming up? That is dependent on you. But we are relying on a state, a smaller state, to help us compute answer for the current state. So here, the smaller state here is I plus 2j, eventually which will progress towards the base conditions of the problem as it gets smaller and smaller. So using those previous states, we are computing the current states. So it's less about future and past, more like, previous state and current state that we are relying on. You can also understand it with a counter example. For example, you want to know what is the best you can do with these elements. To compute what is the best you can do with the elements I to j, you cannot depend on the answer in the range I plus 1, j plus 1, because that is not computed yet. These are the states that we have computed already. So to compute ij, we will rely on these states. That is one way to think. Shall we discuss the remaining points now? I was looking at it like we choose ones, then the smaller subproblems are in the future. The smaller subproblems are going to help you solve the current problem. So that is what you will depend on. Future past is not exactly the right term in all the DP problems. Yeah, you can imagine like recursion. Exactly. You can imagine it like recursion. So to solve the current problem, you need to solve the subproblem. Where is that subproblem coming from? Yes, our base condition will be very different here. So if you understand our base condition, you'll see how this will progress outwards. Okay. So now let's discuss the DP steps, everyone. So obviously here we see that there are overlapping subproblems. We are taking min and max. So we have optimal substructure. We have proved that there are DP properties here. So once we are sure that there are DP properties, now we can start with DP state first. DP of ij is basically storing what is the max sum any player can get in the subarray I to j. We say any player, right? Because if it is player one's turn, player one will get max sum there. If it is player two's turn, player two will get max sum there. Both are playing optimally. Now coming to our DP expression, it will look something like this. DP of ij is equal to max of min of I plus 2j and I plus 1j minus 1. I plus 1j minus 1 and ij minus 2. Now you tell me what will be the base condition here? Or what are the base conditions here? What are the base conditions here? Don't look at the DB expression. Just look at that ij. I equal to j. Perfect, perfect. Exactly. If you have one element only, right? If there is one element only left in your subarray, means I equal to j, then that is our simple base condition. So first base condition for us here is for all I equal to 0 to n minus 1, dp of I comma I is equal to, what should the answer be? Yeah, that's it, array of I. Only one element is there. That is array of ith element. So array of I is the answer. That player will pick that element. That's it. But that is not sufficient base condition. We need another base condition, which is perfect, guys, perfect. Not I greater than j. I plus 1 equal to j, which is only two elements are there. Exactly. If there are only two elements, then what do we do, guys? I equals to 1 to n minus 1. Or 0 to n minus 2 to be precise. dp of I plus 1 is equal to, that's right, max of array of I comma array of I plus 1. Only one element is one base condition. Only two elements present, that is the other base condition. How is it guaranteed that player one will have max? So dp of ij will store what is the maximum any player can get in the subarray I2j, right? So if you give any player the state, tell me guys, where is the answer? dp of, that's right, p1 will start the game. Where is the answer? Answer will be at dp of, just look at the dp state. Maximum any player can get in a subarray I2j. 0 to n minus 1, exactly. 0 to n minus 1. You want the maximum any player can get in the subarray 0 to n minus 1, which is the entire array. And whichever player starts the game, that is player one, they are getting 0 n minus 1 as the state. So whatever is the answer in 0 n minus 1, that is the answer. Okay. Now, if you look at the matrix, basically dp of I, let me draw it as a square. I think that is more appropriate. dp of I cross I is basically along this diagonal, right? And dp of I comma I plus 1 is along this diagonal. And dp of 0 comma n minus 1 is basically here. 0th row, n minus 1th column. Means we need a n cross n matrix here. We need an n cross n matrix here. Table size, integer, dp, array of size n cross n. From the dp expression, can't we get the base condition? No, right? It's dependent on I plus 2 and j minus 2. Maybe using just this, you could probably get it. That is also a bit problematic. Yeah, just 2 diagonals. So that will simplify our process completely. If you look at this, basically what we are doing here is when you are at I comma j, you are basically depending on the cell I plus 2j first. I plus 2j is somewhere over here. And you're depending on I plus 1j minus 1, which is somewhere over here. And you're depending on ij minus 2, which is somewhere over here. Basically, we are starting from middle and going outwards. In general, we start from the beginning and go towards the end. That is right. That is a valid observation. That is what I'm trying to highlight over here as well. So ij is dependent on these 3 cells. So only when they are computed first, after that, we can compute I comma j. It means that this matrix has to be filled. Has to be filled diagonally and diagonally until you reach 0 comma n minus 1. Of course, there are other ways to fill it. You can you can fill it right to left, but come bottom up. You can fill it right to left, coming from bottom to top. Or you can also fill column by column, bottom to top, and right to left. Of course, you can ignore all these indices. Time complexity, space complexity, I think they are pretty straightforward. Number of states into time taken to compute each state. Big of 1, we have big of n square states. And space complexity is basically the table size. And lastly, what about space optimization? Three cross three is perfectly wrong. 3 cross 3 is not sufficient, right? You need to store this entire diagonal, and this entire diagonal. You need to store 3 diagonals, 2 previous diagonals and 1 current diagonal. Yes, but it will be simpler to do space optimized approach. Instead of taking the diagonal approach, you could take the, bottom to top row by row calculation approach. Then you can say that I need to store 1 current row and 2 previous rows. That will be a much simpler approach for you to do in a space optimized approach. Yeah, either way, the space optimized size will be 3, n, 3 cross n. One current row and 2 previous rows. But this you should compute row by row, bottom to top. Make a quick note of it. We'll move on to the next question in 30 seconds. All right. Moving ahead to the next question. For the next question, you're given an array of size n. which contains the sizes of n-1 matrices. Sizes of n-1 matrices means 3 cross 4 is one matrix, 4 cross 6 is one matrix, 6 cross 2 is one matrix, and so on. All these are sizes of the matrix, sizes of different matrices. As you can see, I gave you an array of size 7. So I only have 6 matrices. If I have to multiply the first and the second matrix, then can you tell me what will be the number of iterations that it will take? 3 cross 4 and 4 cross 6 if I want to multiply. How many iterations does the matrix multiplication take here in this specific example? Three cross 6 is the end result, but that is not the number of iterations that it will take. That is right. 3 into 4 into 6 is the correct answer. It will take 3 into 4 into 6 iterations. If you don't know how we got this, then you should probably learn matrix multiplication first before you follow me on this question. So I kind of assume that you know what a matrix multiplication is and how it works, and I am going ahead with that assumption. That's right, 3 into 4 into 6. So to multiply a matrix of size 3 cross 4 and 4 cross 6, it will take 3 into 4 into 6 iterations. Now let's say I want to multiply these 3 matrices. Let's say I want to multiply these 3 matrices. So let's call these matrix M1, M2, M3, M4, M5, and M6. I want to multiply M1, M2, and M3. I can do M1 into M2 and then multiply with M3. Or I can do M1 into M2 into M3. I can do it in 2 different ways here, right? If I go with the first approach, then it will take me 3 into 4 into 6 iterations to compute M1 into M2. I showed you here just above. 3 into 4 into 6 iterations to compute M1 into M2. And the resultant matrix will be 3 cross 6, right? So the result into this will take plus exactly 3 into 6 into 2 iterations. So this is the time taken to do M1 into M2. This is the time taken to do result into N3. If I do it this way, then this will take first M2 into M3 will take 4 into 6 into 2 iterations. And the result of M2 into M3, if you multiply with M1, this is 4 cross 2 matrix. It will take 3 into 4 into 2 iterations. So if you can help me calculate this will be something like 72 plus 36. This will be something like 24 to 28 plus 24. So clearly doing it in the second way will complete the multiplication in lesser number of iterations than doing it in the first way. My calculation is correct, right? Yeah, it is correct. Clearly doing it in the 48. This is 48. That's right. It's not 28. Doing it in the second way will complete our multiplication in lesser number of iterations than doing it in the first way. And that is the question. You need to compute the minimum number of iterations to multiply all the given matrices. Compute the minimum number of iterations to multiply all the given matrices. This problem is known as basically matrix chain multiplication problem. Is the question clear? Did you understand the question? Okay, okay. Yes, yes. Okay, great. Take your time, take a look at it, understand what you can do, understand the question properly in depth. Don't share your solutions until I ask you to share. See how you can break down this problem. observations, solutions, whatever you have. Please share whatever you have figured out. Each matrix can be multiplied to its left or right matrix. That's a good observation, but it's not just left or right. It's not just left or right directly. It can be the left result or the right result. That left result can be a multiplication of any number of matrices. The right result can be multiplication of any number of matrices. For every I, choose many iterations from 0 to n minus 3. Okay, you have the right direction, but you did not choose the right data. Okay, fine. Let's look at it. So did you guys do this step? Drawing it like this? And then thinking, what is the middle of a problem here? So what is the main problem? You want to know what is the main iterations to compute the subarray I to j or 0 to n minus 1. Or in fact, the middle of the problem is what is the minimum number of iterations required to multiply the matrices I to j. That is the middle of the problem here. N minus 3 simply gives the last matrix combination. That is not exactly correct. That's what I will show you here. So when I say I and j here, guys, I and j are not indices. Because we are concerned about the matrices here. We can say that now I want to multiply ith matrix to jth matrix. That makes more sense. If you say that I want to multiply index I to index j, that is not exactly going well with our thinking, because j here is not exactly m4 or m5, right? It is a shared value between m4 and m5. So it is simpler to think of it as matrices instead of indices. I and j are matrices, exactly. So now thinking in that direction will help us simplify this problem here. Now let's say that my I and j are here, okay? My I is here, j is here. I am at ith matrix and jth matrix. I want to know how to multiply all the matrices from ith matrix to jth matrix with min number of iterations. Now, what are my options? I can multiply I to k and then multiply k to j. Or I can multiply I to k and then multiply k to j. Or I can multiply I to k, then multiply k to j. Are you following me here? And then here. Yes. And then here. These are all the possible options that we have, right? For multiplying the matrices from I to j. It means that K is looping from for all the matrices in the range I plus 1th matrix to J minus 1th matrix. Yeah, you can say there are J minus I possibilities. J minus I minus 1, technically. But yeah, that is the number of possibilities that we have here. Only if you understand this step, we can move forward, guys. Please let me know if there's any confusion, if you want me to repeat. Repeat. Okay, I'm repeating once again. Okay, so here, I and J are matrices. They are not indices. Don't look at these numbers now. Look at these. M1, M2, M3, M4, M5, M6. Okay, I is at some matrix, J is at some matrix. Now the problem here is, or the sub problem that we are at is basically, what is the minimum number of iterations to multiply all these matrices in the range I to J? That is what we want to know. So what are our options here? To multiply all these matrices, first I can multiply I to K matrices, and then I can take this result and multiply K to J matrices. Or I can multiply I to this K matrix, and then I can multiply all these matrices. Or I can do it with these matrices. I can multiply I to K matrices and then multiply the result with K to J matrices. To be precise, we are not multiplying K to J matrices, right? To be precise, we are exactly multiplying K plus 1 to J matrices. I to K is one set of matrices, and K plus 1 to J is the next set of matrices, right? That is what we are multiplying here. This K plus 1 could be anywhere from here to here. They could be anywhere in the range of I to J or in between I to J. They can be here, they can be here, they can be here, they can be here. Any more doubts with this discussion before I move forward? Are we breaking it into two sub-problems? Yes. But two sub-problems in one possibility. There are many possibilities. In each possibility, there are two sub-problems. So we should try all those possibilities. So here you have two subproblems, here you have two subproblems, here you have two subproblems, here you have two subproblems. Okay. So now let's try to understand how exactly this will translate to the indices that we have here. Or before that, we will just start, go step by step. Okay, we'll go step by step. For example, I equal to 3, K equal to 4, K plus 1 equal to 5. Oh, you're pointing to these things. Yeah. So you should not again say that I equal to 3. That is wrong. I equal to M1. That is correct. I is not equal to 3. I is equal to the first matrix, 3, 4 matrix. And J is equal to, you can imagine the M4 matrix, for example. Then K will be M2 and K plus 1 will be M3. Yeah, I equal to the matrix 3 into 4. Exactly. Okay. Any more doubts, guys? Cool. So we'll start step by step. Okay. We'll start with DP state. So DP of IJ, what do we want here? Basically, we want to know what is the min cost to multiply ith matrix or all matrices from ith matrix to jth matrix. All matrices from ith matrix to jth matrix. This is our DP state here. Based on what I showed you here just now, we have a lot of possibilities for K. So to be precise, we have our K can move anywhere from K equal to I to J minus 1 or J minus 1. I plus 1 to J minus 1. I plus 1th matrix to J plus 1th matrix. So it's not exactly I plus 1 to J minus 1, because you should also consider the possibility where, what do you say, you're taking ith matrix and you're multiplying with everything from here to here. This possibility should also be considered, right? So it's not exactly I plus 1th matrix. K can start somewhere over here. I to K is basically one matrix. You're taking one matrix and multiplying with all these matrices. So to allow that possibility, we should start from I. Out of all these possibilities that K is looping on, we will take whichever is the exactly minimum of all these possibilities. Minimum of all these possibilities. Now let us consider one possibility here. Let's say that my I is over here. K is over here and J is over here, for example. Means I is at 1, K is at 2, J is at 4. I is at M1 matrix, K is at M2 matrix, J is at M4 matrix. Now, what will be the what will be the sub problem that we have to compute here? First, we should know how long it will take to multiply these matrices, which will be given by dp of ik 1 2. That is right. Ik. Then we should know how long will it take to multiply these matrices, M3 to M4, which will take dp of exactly K plus 1 to J. K plus 1 to J. Now, once you know how long it will take to multiply M1 and M2 and M3 and M4, now you should know how long it will take to multiply these results, right? How long will that take? The resultant matrix will be 3 into 6 here, 3 cross 6 matrix here, and 6 cross 5 matrix here, right? So it is 3 into 6 into 5, which is nothing but array of I is array of 1, array of 4. It is not array of I, right? Exactly. Array of I minus 1. Array of I minus 1, which is 3, into 6 is nothing but array of K, into 5 is nothing but array of J. Exactly. This is the time taken to multiply the two results, IK matrix, K plus 1J matrices. Once you multiply them, you should multiply those two results together. That is what we are computing here. What will be the base condition here? What will be the base condition? Only one matrix. Exactly. What will be the time taken to multiply only one matrix? dp of I cross I is equal to 0. Exactly. That's it, right? 0. One matrix, nothing to multiply. No iterations are required. 0. For all I equal to 1 to n. Or n minus 1 to be precise. Yeah, n minus 1. That's it, right? We don't need any other base condition. Or you can probably write base condition for two matrices as well. What will be the base condition for two matrices? Two n minus 1, I guess. Yeah. Yeah. dp of I cross I plus 1. Or 1 to n minus 2 to be precise. I to I plus 1 is equal to. That's right. It will be simply array of I minus 1 into array of I into array of I plus 1. But most likely you will not need this because that is handled by our dp expression itself. Yeah. So this is also handled by a dp expression. So you will not really need this base condition. And lastly, last important step, which is where is the answer? Answer is it. Zero cross n minus 1. Answer is it. 1 cross n minus 1. Perfect. First matrix to n minus 1th matrix. First matrix to n minus 1th matrix, right? Answer is at 1 cross n minus 1. And we can finish the other things like table size, time complexity, space complexity. And space optimized the table size, I'll leave it for you. So that is matrix chain multiplication, guys. So on a scale of 1 to 10, how confident are you in understanding the DP expression that I wrote here? 10 being, yeah, I'm very confident of why we wrote it like that. 1 being, I have absolutely no clue why we wrote it like that. You can answer, guys. On a scale of 1 to 10, how confident are you about the DP expression? 8, 7, 8, 9, 6, 8, 6, 6. Okay. 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 Okay, great. So please make sure that when you're attempting this problem, you do not get confused between understanding index and matrix. I and J here are not representing the indices directly. They are representing the matrices. Make sure you highlight it somewhere in your notes properly so that you don't get confused later. Can you explain array and the DB expression once again? So you can take this example IKJ here. I is at 1, K is at 2, J is at 4. So these are the matrices that we want to multiply. First matrix to second matrix and third matrix to fourth matrix. We want to multiply all the matrices from first matrix to fourth matrix. So dp of ik will tell you how to multiply the m1 and m2. K plus 1 to j will tell you how to multiply m3 and m4. Now, you want to multiply the result of m1, m2 with the result of m3, m4. Result of m1, m2 is size 3 cross 6. Result of m3, m4 is of size 6 cross 5. So you can see that array of I minus 1 will tell you what is the number of rows in first matrix. Array of K will tell you what is the number of columns in the first matrix and the rows in the second matrix. And array of J will tell you what is the number of columns in the second matrix. Moving ahead in 30 seconds. Eighth matrix is equal to array of K minus 1 cross array of K. Yeah, that is right. Okay, this matrix chain multiplication problem is considered to be one of the more difficult problems under dynamic programming. So the difficulty level for this problem, if I have to rate it, is more like, medium, hard to advanced. So if you understood the DB expression, that is like, understanding 90% of the solution. All the other things, you can do it on your own. They are not very tricky over here. That is the only difficult part here. And matrix chain multiplication has a lot of applications. You can use this idea in a lot of places. To conclude the DP discussion that we have here. So in DP, and basically in dynamic programming, we basically just touched the tip of the iceberg. In all the last 3 sessions, today's last session and the previous week session, we could only touch the tip of the iceberg in dynamic programming. Dynamic programming is so deep that teaching dynamic programming itself will take a 14-week course. But what I have tried to equip you with is I gave you enough tools to start off with any DB problem you come across. I gave you tools to understand how to look at a problem, how to break it down, how to bring it to a DP state and DP expression. And from there, you know what to do. That will not work for every possible DP problem out there, but we covered a majority of the variety to show you how to solve a different variety of problems. DP, based on what I have covered in this course till now, or what we have covered in this course till now, is very, enough, is very much enough to clear your face-to-face interview rounds in companies. But if you try to go write some competitive coding contest like on Codeverse or CodeChef with this knowledge, you will see that you are terribly under-equipped. So if you are going into the competitive coding direction, DP, what you learned here is nowhere enough. If your goal is just attend interviews and get a good job, which is why you are here, that's why I'm teaching you, then what we have is going to cover all the different varieties and all the different concepts, and it will give you enough to start off with, to deal with any problem that you come across in that difficulty level. What you should focus on a bit more, I mean, I can tell you a few more problems, which you can probably learn after the session is completed. You can probably start with this problem of edit distance. So there's this problem called edit distance, which is basically a string based problem. It's a very nice problem. It's a very simple problem. Then we have the string partitioning problem. You remember the string partitioning problem that we discussed using try solution, carry forward, and under tries. So that string partitioning problem is when you already have recursion there, right? So you just have to apply DP on your recursion there. Whenever you're revisiting that state, instead of recomputing it again, you just access your DP table and see if it is already computed and do it. Then you have similarly, I mean, palindrome partitioning is also a similar problem. Palindrome partitioning. Then you have different types of problems like building bridges and box stacking problem. This is a very fun problem, box stacking problem. So box stacking problem is basically taking the longest increasing subsequence problem and putting it in extending it to a 3-dimensional problem instead of a 1-dimensional problem. Then we have rod cutting problem and longest common subsequence between 2 strings, and you can also have longest we have this problem, right? Longest palindromic substring. There is a DB solution also for it. You can try exploring that. And what else is there? Egg dropping problem. Egg dropping problem is not like, n floors and 2 eggs. It's more like n floors and m eggs. So it's a fun problem. It's a nice problem. Egg dropping problem. Then you have largest or basically fastest way to reach the end of the array. It's also known as minimum jumps to reach the end problem. Minimum jumps to reach the end. So minimum jumps to reach the end is basically they'll give you an array like this: 3, 4, 2, 1, 5, 9. So you will start from index 0 always. So if you have 3 here, you can go 1, 2, or 3 elements away from here. Then when you have 4 here, you can go up to 1, 2, 3, 4 elements away from 4. Like that, you will go from one element to the other. You need to calculate what is the minimum number of gems in which you can reach the end of the array. It's a very nice problem. It's a very interesting problem. And actually, it's a very easy problem also. If you just try to attempt it once, I'm very positive you'll get it. And there are different variations in it. Minimum gems, maximum jumps, if it is possible or not, etc. There are a few variations in it. Just make a note of these things. And obviously, I'll give you more problems in the assignments, and yeah, that is also there. Last 10 seconds. Moving ahead to our next discussion. All right, guys. Let's begin with graphs. Let us begin with graphs. A graph is essentially a set of vertices, comma edges. So here the numbers that I wrote are basically our vertices and so on. I usually don't highlight the numbers. It looks cleaner and simpler like this. So all the numbers are vertices for us here, and all the lines are edges. So we know that these are known as vertex or node. And we know these are known as edge or a link. And all the things, all the, what do you say, terms that we discussed in trees are similar to those terms that we will encounter in graphs. So here, any graph is basically a set of all the vertices and all the edges. So this is the mathematical representation of a graph. A set of all vertices, comma, all edges. A graph can have many properties. The first property that a graph can have is it can be directed or undirected. Is it can be a directed graph or an undirected graph. A directed graph is basically a graph where you can only go from 2 to 1, but you cannot come from 1 to 2 unless there is another arrow pointing from 1 to 2. An undirected graph is also known as a bidirectional graph, means the edge from 2 to 1 is also the edge from 1 to 2. Undirected graph, also known as a bidirectional graph. Similarly, can you tell me what other properties that a graph can have? Or just look at this graph and tell me what properties does it have. Cyclic, great. A graph can be cyclic or acyclic. Weighted, perfect. A graph can be weighted or unweighted. Connected or disconnected, great. A graph can be a connected graph or a disconnected graph. More than one path to reach a node is basically cyclic property. All that depends a bit, which I'll discuss in depth. What else? What else can a graph be? What else can a graph be? Can be a tree. Yeah. We will come there. That's a completely different thing. Yeah. So a graph can be a simple or a complex graph. And a graph can be a complete graph. Or if it is a directed graph, it would be a complete digraph. Planar or non-planar is completely different. It doesn't fall in this discussion. So these are the fundamental properties that a graph can have. Now, I already explained you what is directed or undirected. Now I'll show you what is cyclic or acyclic. I'll explain everything, not just the last one. We'll go one by one. Now we are here. Okay, now cyclic versus acyclic. A cycle is basically this in a graph. So if you are able to reach that node from another path, then that is a cycle. Or if you are able to start from that node and end at that node again, that is a cycle. A cycle can happen in any different ways. If I draw, for example, a link here and here, now I can say that this is a cycle. I can say that this is a cycle. I can say that this is a cycle. There are different number of cycles here. So doesn't matter where the cycle is there in your graph. If it has a cycle, it is a cyclic graph. Your entire graph doesn't have to be a cycle for it to be a cyclic graph. You can have a cycle anywhere in your graph. So this graph that we have here is undirected, it is cyclic, and it is unweighted. So weighted or unweighted is basically values associated, or weighted is basically having values associated with edges. So if you say that, okay, this edge has a value of 3, this edge has a value of 5, this edge has a value of 10, and so on, then it would be a weighted graph. The example that I have here doesn't have any values associated with edges. So it is an unweighted graph. How this one is bidirectional. So bidirectional is basically saying that if you have an edge, then it acts as a movement in two directions. An edge from 1 to 6 is same as an edge from 6 to 1. Whereas in a directional graph, you will have the directions, like for example, 3, 1, 2, 5, in this manner. An edge from 2 to 1 is not an edge from 1 to 2. Okay, next is connected or disconnected. The graph that we have here is okay, disconnected. Thank you. Disconnected. So basically, what is a disconnected or what is a connected graph? Let us understand that. A connected graph is basically a graph in which is basically an undirected graph, or a graph basically, doesn't matter. A graph in which there exists a path between every pair of nodes. At least one node is not connected. No, that is not the definition. So if I have a graph like this, 3, 1, 2, 4, 5, 6, this is a connected graph. I can start at any node and I can reach any node. There is a path to all the other nodes. But if I have another set of nodes like this, 7 and 8, now that is not a connected graph. It is a disconnected graph because I cannot reach 7 or 8 from any of these nodes. So this is a connected graph. Let's take another example. If I have a graph like this, 3, 1, 5, 2, 4, Is this a disconnected graph? Or is it a connected graph? You're saying it is disconnected. How do you differentiate it from this? This is clearly disconnected. But you can see that these two are somehow different, right? This is clearly disconnected. But this feels like it is connected, but it is not connected. So in directed graphs, you don't have just connected or disconnected. In directed graphs, we have basically, let me get rid of this for now. We have weakly connected and strongly connected. Strongly connected and weakly connected. So this particular graph is disconnected. That is obvious. But this graph that we have here is actually a weakly connected graph. And if I have to show you a strongly connected graph, then it will look something like this. Something like this. From every node, you can reach every other node. So strongly connected and weakly connected are applicable only for digraphs or directed graphs. If we remove 2 to 4 link, it will still be strongly connected. Still, you can reach every node from